3. We just got finished talking about graded potentials and looked at generator versus postsynaptic graded potentials. And we said if these graded potentials were depolarizing, these graded potentials were depolarizing and strong enough to reach this threshold stimulus over here, then we'll get an action potential. So now we want to look at an action potential. We want to look at these different phases of this graph and see what's happening physiologically. So we want to be able to do three things. First, we want to be able to write the stages and write words for them, right? So we'll have words we'll have words to be able to go off. Then we want a picture of our membrane, so that will be another visual cue. And then we want this picture of our graph. That will be another visual cue. So the first thing that we do is we start with resting membrane potential, which is negative 70 millivolts. This graph is time on our x-axis and membrane potential, electric membrane potential on the y-axis. So some other things that we need to know, that negative 55 millivolts is our, negative 55 millivolts, this is our threshold stimulus, negative 70 millivolts is our resting membrane potential, and positive 30 is our action potential. We'll see what all that means in just a second. Okay, so I have three different phases of my action potential. So the first phase is going to start at that negative 55 millivolts because that's the start of our action potential. And it's going to go up to this positive 30. So our second phase will start where we start going back down the graph. And then the third phase is this point right here. So as you can see, we go past resting membrane potential. We become even more negative during this third phase, and we'll take a look at what that's called. Okay, so let's draw our resting membrane potential. We've seen this a bunch. We have the outside of the cell versus the inside of the cell, and we know the outside of the cell has a ton of sodium relative to the inside of the cell, and this is really what's driving our membrane potential. So we have all these sodiums on the outside and a little bit of sodium on the inside, and then more potassium on the inside than we do on the outside. So this is how you set up resting membrane potential. Now, due to the so many positive ions, these sodium ions on the outside, we're going to call this outside positive relative to the inside. And we're going to say that this difference in membrane potential is negative 7. The difference in membrane potential is 70 millivolts. Because the membrane is 70 millivolts less than the outside electric potential, we're going to call it negative. So we say that this membrane has a resting membrane potential of negative 70 millivolts. Now, the definition of polarizing is to divide or cause to divide into two sharply contrasting groups or set of opinions or beliefs. So in this case, we're saying this membrane is polarized. It's polarized because this is so much more negative than the inside is so much more negative than the outside. So we have this separation of this electric potential, which is why we're saying this membrane is polarized. So this term is polarization, which is causing to be separated into two sharply contrasting groups or sets of opinion or beliefs. That's just a Google definition. But yeah, what we're saying here is that there's this differences in electric potential. So this first phase, and the only reason why I was beating that word polarization for a dead horse is because polarization is in all three of these phases of our action potential. So we need to understand how to separate them. So if we're depolarizing, the depolarization phase of our action potential. So if you've heard of if you detach a marker, cap of a marker, or if you detach the cap off of a pen, that's removing the cap from the pen. If you deter someone from making a bad decision, then you get them to move away from making that decision. Let's try another one. If you demote someone, if an employee gets demoted, that means that they're moving away from what their original position was. So when we talk about polarization, we had this separation of charges, and that was created because of this separation of electric potential due to these imbalances of ions. So if we're moving away from being polarized, being polarized means that we had such a great separation of charges, this was so much more negative. So if we're moving away from being polarized, that means that we're becoming more positive. So depolarization, what's occurring? During depolarization, you have sodium channels open. And when sodium channels open, sodium can move into the cell. So my extracellular sodium out here can move through a channel like this and move into the cell. As you can see, it's bringing this positive charge, and as more and more positive charges accumulate, we go from -70 to -69 to -68, and eventually we get to that -55. So from -70 to -55, these are all just graded potentials. They result in depolarization, but that's different from this depolarization. This is a phase of an action potential. Depolarization in general just means moving from these negative values towards more positive values. So in terms of our phase of an action potential, this is from like -55 millivolts up to +30. You can see all this. So this is our wave of depolarization from right here, this red line, to this purple line. This is where it starts. This is where it stops, from -55 to +30. Okay, so sodium channels are open. We can say that the cell is getting excited. Moving from negative to these positive values. Okay, now we're at +30, and we can see we move back down towards -70 for membrane potential. So this root word re, this means again. So if you've ever had to take a test again, then you've retaken a test. If you retake a test, you take the test again. So repolarization means that we're polarizing again. Remember, polarization just means the separation of charges. So we're having a bigger separation or bigger difference in this electrical potential. So for 2, repolarization means that we're becoming polar again. So polarizing means that we're going back down to these negative values. So this is going to be from like +30 to -70. What's happening physiologically at our membrane? Those sodium channels close, that's the first thing. So since sodium channels close, we don't have positive ions coming in. We also get potassium channels opening. And these potassium channels are going out. So this potassium is moving outward, and it's bringing that positive charge. If a positive charge leaves, you become more negative. So this is how we're getting from our +30 millivolts to our -70. Once we're at -70, instead of closing all this stuff, we're going to do another phase, and that's called hyperpolarization. So hyper means a lot of or high amounts, and to polarize means separate by these charges, so we're becoming even more negative. So hyper means lots of polarizing, so we're even more polarized than we were at resting membrane potential. And that's where this gets confusing, right? Because we've talked about hyperpolarizing a membrane, but a graded potential can result in hyperpolarization of the membrane. So we need to separate results of stimulation, which is basically when you bind a neurotransmitter to a receptor, it's going to stimulate this neuron. That, depending on what channels it opens, that can either be depolarizing or hyperpolarizing. So once you get enough of these graded potentials, depolarizing graded potentials, then you move into the action potential. So what we're looking at here are 3 specific phases of an action potential. Depolarization is a phase, repolarization is a phase, hyperpolarization is a phase. All right, so those are your three different phases of an action potential. And this hyperpolarization here, it's going to result in our membrane being even more negative than what it normally is. So I don't know, maybe it's like negative 90. I don't exactly know what the millivoltage is. Okay, so this idea of threshold, what do we say when we say that we need to reach this threshold stimulus at negative 55? That just means that we need enough, sorry, this was from earlier. We need enough sodium, we need enough graded potentials, we need enough neurotransmitters, so this is what we've normally drawn. We need enough neurotransmitter binding to these receptors, opening up these gates to let sodium in. So enough of that has to happen to get us from negative 70 to negative 55. Once you're at negative 55, it doesn't matter if a neurotransmitter is bound to a receptor. All sodium gates open. That's why we have here sodium gates are open during depolarization. Once you hit negative 55 millivolts, all sodium channels automatically open and sodium can come in freely. So that's this threshold stimulus. All right, so we say that excitable tissues are capable of generating action potential. So what's excitable tissues? Neurons, we just saw that. Muscles, the first thing that we ever did with this stuff was look at a neuromuscular junction with the somatic motor neuron. So we brought this nervous impulse, which we then later called an action potential. That action potential caused movement of extracellular calcium binding to synaptic tagmin, stimulating exocytosis of these synaptic the neurotransmitters within these synaptic vesicles, and then these neurotransmitters will come bind over on this junctional folds, and if you get enough stimulation you get an action potential, which is then going to lead to muscle contraction. So action potentials from a neuron to a neuron is just going to result in another action potential if that presynaptic neuron has enough stimulus coming from it, and then if a presynaptic neuron synapses with a muscle and causes an action potential, it's going to cause muscle contraction. Alright, this is all I wanted to do for this video. Hope it helped. This is phases of an action potential.